As you know, I represent the University of Vienna here. It's one of the oldest universities in Europe, or in the world. In Europe, I think. In Europe. So it was created in, I even don't know how to spell it, you know, so long ago. And I moved there. So University of Vienna created. And I moved there in 2010. And because we have here a kind of special event, so I became the first woman full professor of mathematics in the University of Vienna. So, so you see, yeah, so it's a long way, you know. Full professor of mathematics, no. You're right. You know, University of Vienna is really well known in mathematics, right? Probably you know names of, I don't know, Gödel, Schrödinger, Boltzmann, all kind of famous.
Still the only one?
No, now we have two. Yes, there is also a second one who came after, right? Right. But I'm very proud of this, of course. Great. So today we will discuss exceptional groups. So this will be final part of our journey to random groups, and you will see several new words and a lot of new terminology, but I cannot explain all this terminology. I should say it because I think it is important such that you see that this topic is at crossroads of several other topics like analysis, geometry, topology, K-theory, and everything. So I will try, don't worry if you don't understand all terminology, but I will try to show you kind of essential conceptual points and also attract your attention to some interesting combinatorial issues which we can explain even to first-year students. So I hope we will go like this. So it starts. So we would like to construct some groups with some interesting properties, and we cannot construct. Such groups are not known, and we would like to produce some method how to construct groups we want. Okay, with some specific properties, and one of these properties is geometric and related to the notion of coarse embedding. This is a notion which was defined for general metric space by Gromov, but our metric space, as usual, will be just a finitely generated group. Okay, so a function from this metric space to a Hilbert space. This is a Hilbert space, is a coarse embedding, and the definition is very easy. So if and only it's a coarse embedding if the distance between images goes to infinity, if and only if the distance between pre-images goes to infinity. Okay, that's all. So the function is not continuous, it's not one-to-one, nothing else. Just this very rough condition on distances. Okay, so you can. When you see it first time, you can imagine that, oh, this is really too general, okay? But let us see what we can do with this. So the first example is the free group. As a metric space, you know that a free group is just a tree, right? And you would like to embed it into a Hilbert space. First of all, of course, you have to find the Hilbert space somewhere. In this example, the Hilbert space will be just L2 functions on edges of this tree, on edges of the calligraph. Okay? So real-valued functions such as square summable. Okay? This is our Hilbert space. And the map, so I would like to prove in this example that the free group coarsely embeds into a Hilbert space. And the map is very easy. So so you are in the calligraph, so in a tree, right? There is an origin and there is your element. And because it is a tree, you will find a unique geodesic path from G to the origin. Okay, these are edges in the calligraph, which is a tree. And the map is just taking characteristic functions. These deltas are Dirac functions, characteristic functions of edges. Okay, so each edge goes to in this space to a basis element. Okay, great. So this is the map. We would like to see that it is a coarse embedding. So we would like to take f of g and f of h and compare. So if I have h somewhere, a different element, for this different element I also have a unique geodesic path from the element to the origin, right? And I don't know, it's unique, so it goes somehow, and probably it coincides at some point. Or not, we don't know, okay? It coincides and go to the origin. So for this element, again, it is just a sum of characteristic functions, like it is defined. And now we would like to estimate what is the difference between the images, the norm of the difference. But what is the difference between the images? Okay, characteristic functions here and here. And of course, when you consider the difference, these characteristic functions will cancel. Okay? So what you have just, understand that in this Hilbert space, each edge function on this characteristic function, these are basis elements. Okay? So the difference here will be just, as in a Euclidean space, the vector with the coefficients 1, 1, 1, minus 1, minus 1. Okay? And how many? The distance between these two elements, right? How many? Exactly the number of edges here. So the vector with the coordinates 1, 1, minus 1, minus 1, how many? This distance, the Euclidean norm is exactly the square of the distance, right? If you, you have to take square root to take the norm. The square norm is the sum. Okay, so we see immediately that this is this formula, and okay, let us see the definition. And we see immediately this goes to infinity if and only if this goes to infinity. Okay, so it's a very basic example, but it shows also that other examples you see immediately here. If you have an isometric embedding, of course it is coarse, right? If you have quasi-isometric embedding, just this function will be affine, right? Linear. So of course it will be also coarse embedding. Okay, all these are isometric, quasi-isometric, all these are examples of coarse embedding. So this is a very, very rough condition to be coarse. But this one, for example, is not isometry and is not quasi-isometry. Okay, it is the distortion is square root, but it is coarse embedding. Great. So there are some other examples. I list them here, so if you don't know some words, it doesn't matter. But for some of them, you can do easy exercises. So finite groups, of course, into finite dimensional, for example, Hilbert space. Of course, abelian, free abelian, right? Just embed it into RK, which is also a Hilbert space. For amenable, I don't explain, but if you know what it is, this one free group we just saw, and a kind of generalization of this argument is possible for hyperbolic groups. Not easy, but possible. Okay. So all these are coarsely embeddable also, and another class. If you know what is higher group property, this is fantastic. But if you don't know, you can just consider it as a definition. Take groups. We just had a definition of coarse embedding. And assume that the group acts properly. Assume that group acts on a Hilbert space. And then put this condition that I consider groups which have coarse embeddings equivariant with respect to this action. And this will be definition, which is equivalent to all other definitions of the higher group property, okay? So groups with higher group property, these are groups which have coarse embeddings into a Hilbert space, good coarse embeddings, because in addition, they are equivariant, okay? So conceptually, I think it is okay. And what we are interested in this kind of groups, so finitely generated and even finitely presented groups, which have no coarse embedding into Hilbert space, okay? And these groups were constructed by Gromov, and we will discuss mostly these groups today, the constructions. But first, why we are interested in this kind of strange groups. And here I imagine that most of the notation you don't know, but doesn't matter, okay? I need to say this because this is a big motivation, and you see a little bit of history also. So there is so-called Bohm-Kohn conjecture in topology. The original one is quite old. And there is some map between topological K-theory associated to a manifold where we have G as a fundamental group. And there is also analytic K-theory, which is associated to the sister algebra to reduce sister algebra of this group. So these are quite fundamental concepts, and there is some map, and the conjecture says that this map is isomorphism. Okay, to relate topology to analysis mostly. So it is quite fundamental and still open. This original one still open, and there are some versions of this conjecture. So this is with coefficients. We say, because here you instead of so I will click right. So here you have complex coefficients which we don't write. And here just every sister algebra, group sister algebra, so it is much stronger, right? So we have isomorphisms for every. So conceptually you understand it's much stronger. And then there is so-called coarse Bohm-Kohn conjecture, which is for certain coefficients, for certain particular algebra here, okay? So for the moment, this conjecture is, and there are some other variants also. It's quite a popular topic. And why this is a motivation? So this is a motivation for us because we would like to construct counterexamples. Okay. And why we would like to construct counterexamples? Well, I hope you feel a little bit that it is quite fundamental, but now you will feel completely that it is really fundamental, okay? So this conjecture, actually, it is so strong that if we consider certain parts of this conjecture already, so conjecture says that some map is isomorphism, but even if you prove that it is injective and only for certain coefficients, it's already a very strong result, okay? So in particular, it implies all these conjectures, and the list can be long. So you see that it is a really hot motivation, okay? Great. So, but how it is related to our groups, right? And it is related, in particular, there are some other results, but I give here one example, actually two examples, but theorem of Goulnara, which says, actually he proved coarse Bohm-Kohn conjecture for groups coarsely embeddable into a Hilbert space. And in particular, it implies Novikov conjecture. For groups, coarsely embeddable, finitely generated groups, coarsely embeddable into a Hilbert space. I mentioned here also coarse amenability implies coarse embeddability. I will not define what is coarse amenability. If you would like to discuss it, we can discuss it later. But I'd like to mention it here just because I will mention it later in the talk. and also such that you have a feeling that there is some class of groups for which if we prove coarse amenability, automatically we have coarse embeddability. So it is good to be coarsely amenable, okay, in this setting. And actually, we will see that it is quite important notion, but I don't need a definition here. Okay, so this is a motivation why we would like to construct non-coarsely embeddable groups. Okay, because once we have them, we hope to analyze them to get a feeling of where to go to find a counterexample to these conjectures. Okay, and actually this was already already done for certain conjectures. So this is also shows that the road we took is interesting road and probably will give us some results. So there is a result of Hickson, Vincent Laforgue, and Skandalis, which says that a Bohm-Kohn conjecture with coefficient does not hold for Gromov's monsters. Okay, so it is already a counterexample, but for the strongest version of the conjecture. Okay, it is not the original one is still open. Great. So now just a little bit of terminology. We say coarse monster graphs or coarse monster groups in this topic when they are not coarsely amenable or not coarsely embeddable into a Hilbert space. Okay, so of course you see if we construct something because of this implication, if we construct graph or group which is not coarsely embeddable into a Hilbert space, then automatically it is not coarsely amenable, right? If it is not coarsely amenable, then we can study what happens, if it's coarsely embeddable or not, and we will discuss this a little bit. Okay, so this is the motivation, and let's go to the construction. So what we would like to construct graphs and groups, and but first graphs, and then try to put these graphs inside groups and conclude for groups. Okay, this is a general strategy, and some of these coarse monsters are already known, and we will see that expander graphs will appear. Probably you heard about it. So if you don't know what are expander graphs, just go after the talk and learn, okay? because this is really important for not only for this topic, but for mathematics in general, for computer science, for whatever networks and so on, okay? So this is really something fundamental. And then we will see that how we will discuss construction of Gromov's monster, different types of Gromov's monster. We already heard a little bit in talks about Burnside groups. There are also so-called Tarski monsters. So there is a list of interesting infinite graphs and groups which are already known to be kind of very exceptional. Okay, so we would like to learn them and to use them to produce some other counterexamples and so on. So we are motivated by these conjectures, not only in K-theory, but also in topology and in group theory as well. Okay, so this is a strategy, what I already said. Find a suitable graph. So a graph which will not have, for example, now we focus on coarse embeddings. Okay, so graph which is not coarsely embeddable into a Hilbert space. Then put this graph inside some finitely generated group and conclude. So very easy strategy, but very difficult to realize. Okay, so more in detail. A graph gamma as labeled, and as I told you at the very beginning, infinite union of finite graphs. Okay, given such a graph, we can define a group by graphical presentation. Do you remember how? Do you remember? Okay, so generators of this group are just letters, labels, and relators, everything you read on cycles of this graph. So you have infinite sequence of finite graphs. You read everything on cycles. All this will be your relator words. So very big presentation, but you can define it. Okay. So you define this group, G of gamma. And then study the embedding. So gamma 0, it's a connected component. So you have this finite piece, and you study the embedding. Why I can study the embedding? I mean, why there is a map even from this to this? Just by definition, right? Because on the graph I read on cycles, this is exactly my relators. So by definition, I have some map. I don't know by definition it is injective or not. I just have some map. Probably when I do this map to the Kelly graph, a graph is just completely, destroyed. It's possible. Just by definition, I don't know anything about this map, but I have a map. Here I already put it like injective, because I know that it will be under the conditions we will discuss. But by definition, there is no injectivity. Okay? Great. This is our strategy. And this was the strategy for this Gromov's monster. And the suitable graph we had, actually, the idea of Gromov, is large girth expander. So I will define expander a little bit later. And large girth, what is the girth of the graph? It is the length of the smallest non-trivial cycle. Okay? And large girth means what? Because we discuss infinite graphs, infinite unions of finite graphs. So you consider girth here, girth here, girth here, and it should go to infinity. Okay? This is large girth. Great. And the embedding, so once I have this large girth expander with some labeling, by definition, expander will not have labeling, as you will see. With some labeling, I define this group, and then what will be true, that this embedding is embedding and almost quasi-isometric. I will tell you exactly what it is a little bit later, okay? And then conclude. So conclude doesn't mean it is automatic, okay? So you have to first know, for example, that expander is not coarsely embeddable into a Hilbert space, and it was proved in a quite famous paper by Enflo. Of course, not in this terminology. There was even no terminology coarse embedding at this time. Okay, but he was studying Banach spaces, and actually, what he proved it is this. And because it is known for expander, and because the embedding is so, we can conclude that the group we have here, so actually the Kelly graph, is not coarsely embeddable into Hilbert space. Okay, so we need a lot of things. So we need a graph, we need a labeling, we need to know what kind of labeling, what kind of embedding here we will have, and we need to know that the property we study here in this example is coarse embeddability is good with respect to this embedding. Okay, that it is preserved, because you can embed something as a subspace, but probably your property is not preserved with respect to this embedding, and then you cannot conclude. Okay.
So that large girth condition is on all your finite graph, and then it just goes to the bigger, like the one that you're making. Yeah. So that large.
So you will see in the definition of expander, it is an infinite sequence of finite graphs. Okay? On each finite graph, you can compute the girth, the length of the smallest non-trivial cycle. So it is some number here, some number here, some number here, and we say large girth expander when this sequence goes to infinity.
Yeah, the definition on the sequence. Yeah.
On the sequence, right. Right. It is a little bit confusing saying expander, but actually it is an infinite sequence. Okay? Right. So this is a construction by Gromov, but as usual, not all details were done, and we did actually the important inductive step and also the important part related to randomness. Okay, so we explained this. Great. So, but of course, this is just example of the yes. And I'd like to make this comment that I have a very recent paper with Roman Tessera, where we produce a group, really a monster you cannot imagine. Okay, so we produce groups, many groups. Actually, really the method to make non-coarsely embeddable into a Hilbert space, and containing no any expander inside, even in a very weakest sense. Okay, so it's like completely to produce something we want, really this monster, but not in the standard way. Okay, so no any expander. Why? Because till this paper, expander was the only abstraction people knew for coarse embedding. Okay, and this is why and it is very difficult to embed into a group, you will see. So this is why it was not only in groups but also in metric spaces and Banach spaces theories. It was a question to know if actually it is absolutely necessary to have this expander. And we proved that not at all, and even in a weaker sense. Okay. So this is, if I have time, I will comment more about this recent result, but let us proceed. Okay, so now I want to remind the definition of expander, or give a definition if you don't know it yet. So first of all, a quite fundamental notion of Chigger constant, or isoparometric constant. So it's constant is just so you take a finite graph. Here is a finite graph, and you count this ratio. So you take subsets of vertices of cardinality less or equal to half of the graph, and you consider the boundary. So it is quite clear what is boundary. So you are in the graph. So this is your graph. You take not necessarily connected subset, right? It's just a schematic picture, and the boundary is just you count edges. Here you count edges, how many edges you have connecting a vertex from A to a vertex outside B. Okay, you count these things. This is your boundary, combinatorial boundary. And divide by cardinality of A, and this is this number. You take a minimum. For example, I gave example of computation. Very easy, you can play with it. It's a very nice fundamental concept. Of course, you can again relate it to isoperimetric discussion we had. Okay, it is not for nothing. It's called isoperimetric. So this is a complete graph on n vertices, and this is a cycle. So in a cycle, when you take a subset, of course, you have just two, right, outside. So you see that immediately that in a cycle, the Chigger isoperimetric constant is small, right? When n goes to infinity, it will be going to 0. And in the complete graph, it's not small at all, right? So so you will see next week you will discuss amenability and so on. So it is related, okay? But now let's go to the definition of expander, and it's an infinite family of finite graphs with three conditions. So first condition is very easy, just the degree is bounded of every vertex, okay? Second condition is also very easy, just size going to infinity. And the third condition is the most important. Chigger isoperimetric constant is uniformly bounded from isolated from 0. Okay, so it is infinite sequence of finite graphs. For each finite graph, you compute this constant. You get some sequence, and this sequence should be not going to 0. Okay, so this is why it is called expansion. Meditate a little bit about this definition. It makes and it is uniformly bounded from 0. It means that the boundary is not this ratio will not go to 0, so it is expanding. Okay, this is why it is very used a lot in networks and coding theory and cryptography and whatever you can imagine. Okay, so but amenability, what you will learn, it is the opposite to this. Okay, great. So these are graphs, and it's quite useful. And what we will do? Yes. So I'd like to remind you what kind of embedding we discussed. So again, now it is a sequence of, imagine this is our graph, infinite sequence of finite graphs. So each graph, of course, has a metric, right? You just count edges. So you have this sequence metric of metric spaces and another metric space, and what kind of embeddings you can consider. So there is isometric embedding when you preserve distances, right? Quasi-isometric embedding when the bounds between images and pre-images, the differences are linear, right? This is quasi-isometry, what is a linear difference actually. And coarse embedding, I wrote it here in a different way, but it is the same definition. That actually the functions you have lower bound and upper bound, these are just proper functions. What it means is just with the argument it goes to infinity. When argument goes to infinity, the function, the value will go to infinity. Okay, if and only if. So it's very easy definition, and you see immediately again that all these are examples, but it is much more general. Okay, and I remind you again this example we did at the beginning. So and very yes. So because we are here, I think I should give this comment. So what? Of course, if you consider this kind of embedding, immediately you would like to know. Okay, I embedded like this, but is it possible to embed better? Right? Is it possible to embed quasi-isometrically? And actually, it is quite a consequence of extremely famous result of Jean Bourgain, who is a professor just there, right? That it is not possible. Okay, so for the tree, it's not possible to embed tree in a Hilbert space. So it's an interesting topic to consider all kind of embeddings and optimality and so on. Great. So a little bit more types of embeddings. I promise to you that I will define almost quasi-isometric embedding. This is for large girth finite graphs. So you see the formula is almost like in the definition of quasi-isometry, right? But an additive part here, actually not a constant. It's not a constant, but it is small with respect to girth. This is why we take large girth finite graphs. This is looks like technical, but actually it's quite fundamental here in this topic. So almost quasi-isometry, when I will say this is this definition. So upper bound is really like by Lipschitz, and lower bound here it is linear, but here it is small with respect to girth. Okay, and this is again a particular case of even more general definition, which is called unfortunate name because it says nothing, weak embedding, but it is which is more general, and the result I already mentioned, that even in this more general sense will not have expanded in this recent result with Tessera. Okay. And an exercise I gave to you, not very difficult, but very instructive, I would say, to prove that if you have a space where embedded weakly and expanded, then this space will not have coarse embedding into a Hilbert space. So this little exercise was the only known abstraction actually to produce spaces which are not coarsely embeddable into Hilbert space. People took different kind of expanders and tried to embed them into spaces they wanted to study, and then conclude that these spaces are not coarsely embeddable. Okay, till our result, it was the only way. Okay, great. So now let us discuss a little bit these two results. one is geometric small consolation theorem, and another one graphical small consolation theorem. Okay, so what is the setting? Now, we know that expanders are good by result of flow. And we would like to embed them. We know how to define the group, right? And we would like to analyze the embedding. Is it embedding the map I told you that starting from the graph, I have a labeling. I put it into graphical group. I have a map automatically to the Kelly graph. So my graph I started with is automatically in the Kelly graph of the group I defined, but I don't know how. Okay? So I'd like to guarantee that my embedding is good. And these two theorems says that it is possible, but they say in a very different way, and this is what I'd like to explain to you. Okay? So start with a graph as labeled. Labeling is reduced, you imagine what it is, with a suitable geometric small consolation condition. I didn't give you a definition of geometric small consolation, just explained that, okay, for groups acting on some spaces, there is still a way to define what is a relator, what is a length, and what is a piece. And once you have it, you have some definition of small consolation, okay? So it's very, and also I told you that it is very general, so it encompasses all, most of other. Okay, now start with a non-elementary hyperbolic group, so arbitrary, not necessarily free group, okay? Then you can define again a graphical presentation, okay? I explained to you how to define a graphical presentation starting from the free group. But you can also do it starting from any group, right? You have a group, you have a graph. The graph is labeled by generators of the group. You add these relators, so you have a quotient of this group, right? So you can define the graphical presentation, and the theorem says that two things. This graphical presentation will be direct limit of Gromov hyperbolic groups. What it means? It means you have your infinite graph, right? Infinite sequence of finite graphs. So when I add all these relators, I will get infinite presentation, right? But if I cut a infinite piece, I add just a finite piece, I get some finite presentation. And the theorem says that each time you have this finite presentation, the group will be hyperbolic. Okay? So it's really, remember, yesterday we discussed that infinitely presented groups in the space of marked groups are limits of groups which you get when you cut the presentation. It's exactly this situation. Okay? So, okay, so this theorem is a very general small consolation condition, a very general setting here because you can start with any hyperbolic non-elementary, and you get as a result that the graph, each connected component of the graph is injective and almost quasi-isometric. Okay. Now let us discuss the second theorem, which is graphical small consolation theorem. Here, geometric and graphical refers just for small consolation. Consider the graph again, and graphical small consolation, which we discussed in detail, right? And you did even exercises. Then again, you can define the group. Now, this time the group is of a free group, as we discussed. It's a graphical presentation of a free group. So you start at a free group, and you added all these relators. Again, it's a direct limit of Gromov hyperbolic groups, and each component is injective, and each component injects and isometrically. So really very strong. But for this strong, you need graphical small consolation condition. It is natural that you have very strong condition on combinatorial condition on relators, you have very strong conclusion. Okay? Great. I'm not sure I will have time. I wanted to explain to you why here it is injective and isometric. Let us see. If I have time, if we have time at the end, we will discuss it again, okay? But for the moment, I will proceed. Great. So you see differences and analogies between these two things. And there are several names again, because first it was not so you know, always we need to add details. And here is my former PhD student, Dominic Gruber, who added to this result the following thing, that when we discussed graphical small constellation, I told you that you can add also graphical small constellation up to automorphisms. And this is quite important, actually. It's a little technical thing, but it is quite important, as we said already, to discuss groups with torsion and so on, okay? So this was essential. And let us proceed. So it's a little bit complicated, but a very quick sketch of the proof of a very general theorem. Again, you can start with any non-elementary hyperbolic group, and you have, if you have geometric small constellation, you can produce a good embedding, okay? And it is quite involved, but what is probably I'd like to mention here, because we discuss it in the other proof, that still we use this local to global principle, which is quite important in the whole theory, okay? So this was the sketch. Now, okay, we discussed all this. All this is fantastic, but you can say, where is the randomness? Right? So is the randomness here? No, almost quasi-symmetric embedding, there was no randomness. It was just additive constant of the girth and should go to 0.
The limit thing?
No, limit was just you have infinitely many relators, you cut infinite path, and you have your limit. Limit was very concrete in the space of, it's like you start with a group, you quotient, and then you have the limit group. No randomness there. Constructing expanders, this is nice. Unfortunately, it will not help. Exactly, constructing expanders. So expanders first were constructed randomly, by random arguments. By the way, some papers mention Pinsker result 1973, but actually it was later found by Gromov and Larry Good that it was written already in the paper by Barzin and Kolmogorov, which is 10 years almost before Pinsker, in a different more topological way, but also random argument. Yeah. So this was the existence, but unfortunately you will see that it will not help us. Why? Because here, this is an important point, we want to have not like any expander. We would like to have specifically with large girth, okay, and even a little bit more, I will tell you. So this random stuff will not help, unfortunately, but it is like conceptually right. You can say, okay, I know by random things that expanders exist, and then I can proceed. So there is a little randomness here, right? And where else? Where is really essential? Where it can be? Again? Small constellation, right? So so here you see we have very nice conclusions, right? Really nice conclusions. These are general theorems. You can use them for some other things, right? So very nice, but there are assumptions, of course. Here there is assumption suitable geometric small constellation condition. Remember, in the definition of expander, there is no labeling. It is about how it is. It is a combinatorial thing, right? So, and here there is a assumption graphical small constellation condition with automorphisms, right? But still, we need it, right? So, and this is not easy. In the examples, in the exercises you did, you can imagine them graphically. What it means? It means that, for example, in your list of exercises I gave you, there are explicit presentations, right? And you can write related words on cycles. This is your graph. Bigger and bigger cycle, okay? But as we saw, bigger and bigger cycle, it's not expanded at all, okay? But this bigger and bigger cycle, you can write these words explicitly, right? A to the power, I gave you the formula. Yeah, a to the 7, b to the 7, everything to the power n. You can write explicitly. But here, and check that it is small consolation, right? But here, explicitly, it is complicated, and for the moment, it's not known at all, right? So this is why we need actually a little bit more from the graph, and we need the following thing. So this is a notion of DG bounded graph, and why DG bounded? It's diameter girth. So the condition is that diameter of the girth, so again, you have infinite sequence of finite graphs. Each time it's a finite graph, you can compute its diameter and girth, and so it is some number, and you would like to have this number uniformly bounded, okay, from above. This is DG bounded, and as we said before, we need also large girth, right? By the way, you can meditate a little bit about this large girth. Actually, if you don't have large girth, you don't have small consolation at all immediately. You just by definition you see, okay? So so we need large girth DG bounded graph. Why we need it? Because of these two theorems. So one theorem, these two theorems are very nice but different. I'd like to show you, to explain you really they are different. So one is with probability 1 a random labeling of some subdivision actually of such a graph, but uniform subdivision. What it means? Okay, you started with something large girth DG bounded, okay, and then in the proof just we need to subdivide each h into some number, but this number is bounded uniformly. Say each h will subdivide into 100, okay, but it will be the same everywhere. This is important. So the same everywhere, so it will not destroy the story actually. If you have not uniform, then it will not be expanded anymore, okay. So it is important. So it's not very big, but to be clear, I wrote it. It's not a big deal. And then, this generic labeling will have geometric small consolation.
So you do the subdivision and then you label
to prove that with probability 1, you need this subdivision.
Yeah,
right.
With the labeling.
Yes. So this was kind of a completely missing part in Gromov actually. Of course stated and explained, but not technically not present. Okay, so now there's a more recent result of Sider which proves with positive probability there is a subsequence. Here also, like in our case, we did uniform, we need to subdivide a little bit. He needs to take some subsequence, but it's also not a big deal. It's really, some graphs even he does not need to take subsequence, okay? So it's not a big story, but I should write it to be careful. And subsequence such that it has graphical small consolation, okay? But there are differences. It is a positive probability, this is genericity. So this is almost every, this is existence, okay? So now, this is randomness. This is the point where randomness really important. In his, you see in your exercises Lovash local lemma. This is just he used this lemma to prove this result, probabilistic result. Okay, and this was the difference. And we make counting, and we don't use Lovash local lemma. You can, this will be really a fantastic exercise take the lemma I formulated exactly like it is written and try to prove, because you know what is graphical small consolation by definition, try to do the proof, okay? Not see in his paper, right? Try to do your proof. Yeah. Great. So now we have labeling, we can conclude, right? We can conclude. Let me show you again these theorems. Now we have everything we need, right? Right or not? What is missing?
The reduction
In the conceptually, in the ingredients, what is missing? What we need?
You
didn't explain what is the suitable geometric small cancellation.
No, I didn't. It's quite complicated. We don't have time. But I mean, I explained it conceptually, right? So again, we start with a graph. Take an expander. We would like, for example, a monster, right? We make, by the results I just explained, random labeling, and then we apply this theorem, right? And then we conclude by inflows result. But we need an appropriate expander. Remember, here we need large girth DG bounded, okay? So this randomness for expanders will not have these properties, okay? So we need such an expander, for example. Or if you don't need expander, you need some other property, you need such a graph to make the whole story work, okay? You need a graph, large girth, GG bounded graph to conclude, right? So for example, we are lucky because for expanders it was done before, and this is a famous result of Lubotsky, Philip Sarnak, and Sarnak another professor from here, right? So it's really very related and very hot stuff. So there are expanded and even explicitly large girth DG bounded, okay? And actually it is a nice research problem to find if you don't need expansion but just large girth DG bounded, to find an easy way to produce such graphs, okay? It's a combinatorial problem. Okay, so then if we take this such an expander, put a generic labeling, start with some hyperbolic group, put a generic labeling, then by this theorem I explained just before, we have almost quasi-symmetric embedding, and almost quasi-symmetric embedding, actually this will be the fact that expander is not coarsely embeddable, this map preserves. So the group you will get is not coarsely embeddable, okay? And this kind of groups are called Gromov's monster now. When you start, when you do this generic labeling, so when you have almost quasi-isometry here, okay? These were initial construction, and now using these more recent labelings, one can take again the same expander, but prove the existence using Lovász local lemma. Take this suitable existence, right, with positive probability there is a labeling. Take this labeling, and then you have here even isometric embedding, okay? For conclusion, the fact that the group is not coarsely embeddable, by the way, here your group is free, right? You start with a free group. I mean, not the group is free, the group is graphically presented group defined by this expander, but you start with a free group, okay? But the fact that it is not coarsely embeddable, actually you don't need this isometric, even weak, as I told you in the exercise, even weak embedding of expander will be enough, okay? But it is nice to have it, sometimes it is useful, okay? So, right, so, okay, so these were first examples of groups non-coarsely embeddable into Hilbert space. They contain expanders. They even have property T. This is a different story if you combine it with the fact that actually random labeling produce a property T group even when you do it using expanders almost immediately, almost on the first step. Okay, so of course, and then quotients of property T group are property T, so it will be property T. Okay, and then there are some recent results like this, that graphical small. I'm talking now about special Gromov monster, right? About graphical small consolation. So a recent result says that actually graphical small consolation groups are cylindrically hyperbolic. So there is some nice space around. And it means that these two classes I explained, Gromov's monster and special Gromov's monster, they are really like different. Okay. So it's very nice to study both of them actually. Great. So this is a little summary. I'd like to, even if you don't know all words, but just intuition a little bit. So there are 4 properties which are kind of going together. Okay. Amenability, coase-amenability, high group property, and coase-embeddability. What we discussed now, these are groups which are not here, right? Not coarsely embeddable into Hilbert space. And this was like interesting to understand. Actually, these were kind of quite famous questions to understand what is the relation between these things. Okay, is it possible to construct a group which is coarsely embeddable but not coarsely amenable, for example? Okay, so now we know the answer is no, and these are different papers and a lot of work actually. So as I said, here Gromov's monsters are groups which are not here, right? But to produce these examples, we need to produce groups which are not here, right? Which are not coarsely amenable. And there is a lot of terminology for this. Also, it's related a lot to sister algebras of groups. And these groups also called sister exact. It's just synonym, right? Sister exact. So if we would like counterexamples like this, we should produce groups which are for example, high group, but not sister exact. Okay, this kind of stuff. And remember the strategy. Okay, I will mention this the 2 results. So we produced an example like this for high group and non-sister exact. And this one I already mentioned to you. And these are groups. Remember, here it is high group property. I told you, even if you don't know, but these are groups which have coarse embeddings, even good coarse embeddings, because they are equivariant. Okay? Because they have coarse embeddings, you cannot construct this kind of stuff with expanders, right? Because expanders are not coarsely embeddable. So you need some other graphs, and you need some possibility to label these graphs and to produce these graphical presentations, right? So it is again the same strategy conceptually, but realization is very different. So conceptually it is the same strategy, like you need to find some graph first, then a labeling, put it into graphical presentation, and then conclude. Okay? And for coarse embeddability property, your graph property, combinatorial property you needed was expansion. And even our theorem says that probably not, but expansion was enough, right? But if you would like to have some other properties, you would like to produce some monster, your monster, okay? If you can encode it combinatorially somehow in a graph sequence like this, you can try to use this method, okay? So for this non-coarse amenability or synonym non-sister exact, appropriate combinatorial property was this one. Very easy combinatorial condition. So infinite sequence of finite graphs, girth going to infinity, and the degree of each vertex at least 3. That's all. So it's very, very easy. In particular, it is very easy to produce such examples. I don't remember, right. Such examples, how? So take a free group. Free group is residually finite, you discussed it. Take any sequence, sequence of normal finite index subgroups, nested trivial intersection, right? Take quotients, successive quotients. What you get? You get finite groups, right? Infinite sequence of finite groups. You can take any sequence like this of a free group. It will be like this. Girth going to infinity. Understand what it is. Girth going to infinity is just combinatorial way to say that free group is residually finite. Right? Because you take a ball, and a ball in the free group, it is just a finite tree, right? And you will find this finite tree somewhere. In this graph you get. In this graph you get, it is finite quotient, right? It means that in this finite quotient you don't have loops, because you have exactly the same ball. So girth going to infinity. It's just the same. Okay? So this kind of graphs is very easy to produce. You don't need randomness or complicated things. Okay? But of course, if you would like to have DG bounded in addition, then it is an interesting combinatorial problem, right? Okay, and I see that I am quite late. You understand the strategy, and the things we construct now, not with expanders, but with these sequences of graphs called higher group monsters. Let me see if we can go somewhere. Okay, I gave some details here, but you understand there are this is a summary of this about exceptional groups, but you understand this two recent results I wanted to communicate about higher group monster and the monster which is true coarse monster, not containing expander but not embeddable. But there are still interesting questions we can discuss later, because, right? So if you are interested, then we will discuss. So we produce these two counterexamples, and here is last thing. I'd like to summary a little bit all these 4 lectures. So we discussed typical and exceptional groups. And this is just a sample. There are some other models, and there are still models to produce. Okay, so you have something to do. Okay, so typical is almost all. It can be finitely presented or finitely generated. Infinitely presented groups are very interesting in this area, and exceptional groups. I discussed today only exceptional groups in the relation to metric properties, to coarse properties, but it can be also something completely more algebraic or more analytic. Okay, so you take your favorite group you would like to produce and think if you can adapt the technology. And there are some interesting still questions with respect to this now classical models, but also like to produce new models. Okay, and this is the end. Thank you for your attention, and this is